Okay, let's open up to page 244. We're going to take a look at 3 more examples. Yes? You need the notes. Oh, you're passing. Okay. All right, on Friday, we were kind of not necessarily introduced, because you've seen rational functions before, but it's the first time that we've seen them this year. And I'm not quite sure how far you went with rational functions last year. I kind of got the vibe on Friday that we've seen asymptotes before, so that's a good thing. But we're going to dive into different properties of these rational functions as this unit goes on. So on Friday, we were just getting used to the basic kind of shape of or characteristics of a rational function, how we have asymptotes, sometimes we can have holes, and we spent the majority of Friday using our kind of number line analysis, trying to figure out where is this rational graph above the x-axis, below the x-axis, on the x-axis, maybe where it has a hole, where it has an asymptote. So we're going to take a look at 3 more today, but we're not going to have a graph or kind of those step-by-step hints for us to use. Good morning. Anything for the office today? I think we're good. Thank you. Have a good day. All right. So taking a look at the first one, let's first kind of identify what we're trying to find based off the way this notation looks. If we want this rational function to be less than or equal to 0, can we kind of jot down what we should be looking for on a graph? Or maybe based off of our sign analysis, our number line. If we want to be greater than or equal to 0. Yeah.
Where the graph is above the x-axis.
Above. Okay, so that's the greater than part. And if you equal it, yeah? 0 or where it's on. Right, so above or on x-axis. So once we complete our sign chart, our little number line chart, we're going to eventually look for where it says positive, because that's where we would be above the x-axis, but we also have to make note of where we would be on the x-axis, because maybe we can make sure that that's a bracket in our notation. The question is, how do we find those kind of special numbers that we write on our number line? Where do we know where we can kind of stop or pick a number in between to help us get the positives and negatives? Yeah? We got to figure out where the zeros are located, meaning in the top of the fraction or the bottom of the fraction. So if we look at the top, can we think of a number that we could plug in that would make the top 0? Yeah. 3. Okay. Now since there's only one x in the top, that's probably going to be our only answer for the top. On the bottom though, notice how we have x squared, so we kind of have 2 x's to try to figure out in this case. How do you want to figure out what makes the bottom 0? We can guess and check for a while if you want to try that method. Yeah? Quadratic formula, because it's squared. Okay. Maybe we'll try to factor first. Sometimes that might be a little bit easier. Who knows? Okay. Can we think of 2 numbers that multiply to 2 but add to 4? No. Okay, so at least we tried to factor. But since factoring doesn't work, Adam suggested the quadratic formula. So maybe we'll try that real quick. All right. X equals, we need the opposite of b, plus or minus the square root, b squared, so 4 squared would be 16, minus 4 times a times c. So 4 times 1 times 2 would be 8, and that's all over 2a. So 2 times 1 would just be 2. All right, now inside the square root, we'll end up with 8. And since we can't find the square root of that fairly easily, that means we're going to get a decimal answer as our result. Let's just maybe go ahead and use a calculator to get those values. So if we do -4 plus the square root of 8 divided by 2, we'll have negative 0.586. Maybe if we round it. And then we'll do the other option. We'll have negative 4 minus the square root of 8 divided by 2. Negative 3.414. All right, so those are two numbers, kind of not ugly numbers, okay, long decimal values, that would make the bottom 0. Can we classify what these different numbers are? Okay, are they the location of an x-intercept? Are they the location of a vertical asymptote, of a hole? Okay, how can we pinpoint which one's what? What do you think, Alex?
They're vertical asymptotes.
Which ones? We have the 3 and then these two numbers here.
The other two.
These
the
ones?
On the bottom,
Okay. How'd you know those are vertical asymptotes?
because to be a hole, you have to have the top and bottom both be the same number.
Okay, so that's like 0 over 0. Good. And then vertical asymptote would be,
When the bottom's 0.
but not the top. Okay, so a vertical asymptote is if you were to plug in this number, it would make the top part of a fraction be a number, but the bottom part of the fraction be a 0. Okay, so we'd have a number over 0. This 3, on the other hand, it would make the top 0, but not the bottom, because notice how 3 was not included in this list. That would make the bottom 0. So if we have 0 over a number, what's at that location? Yeah. An x-intercept. Okay, so at least in this example, we don't have any holes. There's no number that makes the top or the bottom 0. So now that we have these different locations, bless you, we're going to use these in our number line to help us figure out positive and negative. So in order, we'd have negative 3.414, negative 0.586, and then 3. Now I know the numbers are kind of long, or decimal values might be a little confusing, but we don't necessarily have to plug these in to get our positive and negative results. You just need to pick any number you want, in this case between negative infinity and negative 3.414. So make sure it's an easy number that you pick. Can we think of something in there that might be easy for us to use? Any number between those? Yeah? Negative 4. Okay. So if we plug in negative 4 up top, that would be negative. And then we got to figure out if we plug in negative 4 on the bottom. So negative 4 squared would be a positive 16. And then we're going to add 4 times negative 4, which would be a negative 16. So really those would cancel out, positive and negative 16. And if we add 2, that would be positive. So we figured out the individual sign, like of the top and the bottom, but if we actually divide them, negative divided by positive would be negative. Okay, so we're going to kind of repeat the process, pick an easy number that you can plug in to get your signs. What about something between negative 3.4 and negative 0.586? Yeah? Negative 1. Okay, so negative 1 up top would be negative. Negative 1 on the bottom. Let's see. Negative 1 squared is 1. Then we'll subtract 4, so it's negative 3. And if we add 2, we're at negative 1. So negative on the bottom. Divided together, though, this interval would be positive. What about something easy in the next interval? Yeah? 0. All right, 0 up top would be negative. 0 on the bottom, we just have 2. So overall will be negative. And then for the last interval, anything bigger than 3. Maybe we'll pick 4. So positive up top and definitely positive on the bottom. So positive overall. Coming back to us from Friday? Okay? All right, so we want it to be above or on the x-axis. So if we're above the x-axis, we know our values should be positive. So we have two intervals that we have to kind of include here. But then we're going to use this on x-axis description to help us figure out, can we have a bracket, can we not? So for this first interval, can I include negative 3.4? Am I on the x-axis at that spot? What did we classify this negative 3.414 as? Yeah. It's a vertical asymptote, which means you can't include it. There's no physical point there. You have that dotted imaginary line on the graph. There's no physical graph at that spot. Kind of the same thing going to happen at this negative 0.586, because that was another vertical asymptote. So that interval has two parentheses. The other interval, though, can we include 3? Yes, because we listed that as an x-intercept. We are on the x-axis. So that will be a bracket. And if this interval can go on forever towards infinity, we'll have to end with a parenthesis. So using the number line, we're going to have that advantage to help us write this interval. So we'll have parenthesis, negative 3.414, and then the negative 0.586 with a parenthesis, throw in the u, and then bracket 3 comma infinity. Okay, so without a graph, okay, no graphing calculator necessary to get a picture, we just determined where this graph is positive or on the x-axis. Okay, now we can throw kind of a scenario behind this, kind of a real-world application, and we know this is where our interval would be positive. Okay, having a positive value as an answer. I don't know what that real-world scenario would be for this particular function, but if we did have that behind it, we could use that to our advantage. Let's go ahead and try the next one. Can we find those special numbers that make the top 0 or the bottom 0? What do you think, Adam?
So to make the top 0 would be 3 and negative 1/2, and then for the bottom to be 0, it would be negative 2.
All right. This one was kind of simple for us because notice how it's already factored. We can easily determine what makes each individual factor equal to 0. So now that we have those numbers, let's identify what characteristic they would be on the graph. You have one of 3 possibilities. So it's either an x-intercept, a hole, or an asymptote. Can we label them? 0 over number, x-intercept. Number over 0, vertical asymptote. 0 over 0 was a hole. I'm going to start with this negative 2. Negative 2 was a number that made the bottom 0, but not the top. Yeah. That's a vertical asymptote. So you'd have number over 0. 3 makes the top 0, but not the bottom. So that would be 0 over a number. That's an x-intercept. And then the same thing's kind of going on with negative 1/2. Makes the top 0, but not the bottom. So this is another x-intercept. All right, so no holes in this graph. All right, let's go ahead and check out the inequality. If we want to be less than 0, can we list what we should be identifying after we do our number line? What are we looking for? Yeah.
Any numbers that are below the
X-axis? There you go. Okay, below x-axis or negative, okay, because we're going to have that kind of word pop up on our number line. Okay, so below or negative looks good. So let's try to figure out these intervals. We'll create our number line. We're going to break it up in order with these 3 special locations. So negative 2, negative 1/2, and 3. What are we feeling less than negative 2? Want to do negative 3? All right, if we plug in negative 3, our first factor will be negative. If we plug in negative 3 into the second factor up top, it's going to be negative, but if we square it, because we have that power of 2, it's going to be positive. A negative times a negative is going to be positive. And then if we plug in negative 3 down below, that factor would be negative, but again, we're squaring it, so that's going to make it positive. Is there a little shortcut we might be able to use if we have a power of 2? Yeah? Why? That's good. Yeah. It multiplies itself. So if you plug in a positive times a positive is a positive, and if you plug in a negative times a negative is still going to be a positive. So kind of a rule of thumb is if you see that power of 2, you can automatically just put positive. Okay, it doesn't matter what you're going to plug in. Now, we still got to calculate the overall sign though. The top would be negative, bottom is positive, so after we do the division, we'll be negative. Do you guys think you can do the rest of the intervals? See what you get? All right, I got negative, negative, positive, positive. Check out. Okay, so we want to be below, aka negative. So we're going to focus on those intervals. And now we got to figure out brackets or parentheses. Can we include any of these? So our first interval will never ever reach negative infinity. So that would be a parenthesis. This negative 2 we identified as a vertical asymptote, meaning there's no physical graph there. So there's no way we can count that one. And we would have to use another parenthesis on the next interval because it's at that same spot of negative 2. Now this negative 1/2 we said was an x-intercept. Can I include that spot? Are we below the x-axis at an x-intercept? If you're on the x-axis, are you below it? No. Okay, so we cannot include that one either. We're strictly looking for points below it, not necessarily on it. So it looks like we're going to have parentheses all the way across these intervals. So we'll write negative infinity to negative 3, throw in our u, and then, I'm sorry, this is negative 2, and then negative 2 to negative 1/2. So far, so good? All right. We're going to try one more at the bottom. How is this one a little bit different than the previous two that we just did? We're still dealing with fractions, but it's a little different. What do you notice, yeah?
Because both sides have a fraction on it, one side doesn't have 0.
One side doesn't have 0. Okay, we always usually, notice how when we are factoring, we always want it equal to 0. That way we can break it up and solve. Kind of the same thing's going on here. We want it we want to compare it to 0. That way we know if we want to be above or below or on that x-axis. So somehow we got to get 0 on one of these sides. And how might you want to do that? Yeah? Yeah, so it doesn't matter which one, okay? We're more often used to having 0 on the right-hand side, so why don't we take this fraction and subtract it over? Okay, that way we get 0. Now I'm going to write that over here just so I have a little bit more space. All right, so I'm going to subtract the fraction to the other side, which means I'm left with 0 on the right-hand side. Now at this point, since we have 0, we might be able to determine what we're looking for in terms of above or below. So if we want these fractions to be less than or equal to 0, we want to be below or on the x-axis. So it's starting to look familiar to the previous two that we did at the top, because now that we have the 0, but it's still slightly different. Do we notice anything else that might be a little different than what we've done before? It's starting to get there though, yeah.
So you're subtracting two different fractions.
Notice how we have two fractions here, even though we were just dealing with one kind of larger fraction in the previous two. So if we're really familiar with using one fraction and using our number line on that, what if we tried to combine these here? Can we subtract these two fractions? Yeah?
No, because they don't have a common denominator.
They don't have a common denominator, but can we get them to have a common denominator? How? That's the question. Maybe I'll use a number example. What if I had 1 over 3 minus 1 over 2? Okay, not a common denominator, but how can we get them to have a common denominator? Yeah.
You just find out least common multiple.
Least common multiple, which would be,
Or 3x maybe 6.
it'd be 6. Now in numbers, that's kind of easy to find a multiple, but when you're working with factors or variables, that might be a little tricky. So a kind of a shortcut here is if you take this denominator, we're going to multiply that by the opposite fraction on top and bottom, and then we'll take this denominator times the other opposite fraction on top and bottom. And notice how that will give you that least common multiple of 6 in this case. So it looks like over here we'll get negative 1/6. We can do something similar for these fractions. Okay, we're going to take this denominator of x minus 1 and multiply it on top and bottom. And then we'll take the denominator of x plus 2 and multiply that by the opposite fraction on top and bottom. Can we make that connection between numbers and variables? You see how it's the same concept? It's just one has the variable x and the other one's just dealing with values. Okay, but it's still getting a common denominator. Okay, now we got to think about if we're multiplying on top and bottom, we might have to do some distribution here. We're going to take 3 times x, so that'd be 3x, and then 3 times negative 1, so that'd be negative 3. And we're going to do the same thing for the numerator of the other fraction, but this time we got to take negative 2 because we're subtracting. We'll do negative 2 times x, so negative 2x, and then negative 2 times positive 2, which would be negative 4. What do we do with the bottoms? When you subtract fractions, you subtract the tops, but what do you do with the bottom? Yeah? It stays the same. Okay, you keep that common denominator all the way through. So notice how in our number example, we subtracted the tops, but we kept the common denominator. So looking at what we have here, our common denominator would be a factor of x minus 1 and the factor of x plus 2. You could multiply them out, you could FOIL, but we're eventually going to have to factor back anyway to get those special numbers for our number line. So I suggest keeping them as factors if you can, just to save you some time kind of down the road. All right, maybe we can keep going with the top though. We can combine some like terms. 3x minus 2x would be 1x, and then minus 3 minus 4 would be minus 7. All right, so here's our one fraction. We started with two separate ones, but after we subtracted, got a common denominator, all that jazz, here's our final fraction. And we want it to be less than or equal to 0. So now it looks exactly like the examples we were doing at the top of the page. Okay, one fraction compared to 0. Can we find those special numbers? What makes the top 0? What makes the bottom 0? X equals, can we find them? Good, Alex?
7,
7.
1, and -2.
There we go. Okay, so in terms of our number line, we're going to use those to break it up in order. So -2, 1, and then 7. Can we list what these special locations are? Either a vertical asymptote, a hole, or an x-intercept? You want to try it, Tanner? Yeah.
2 vertical asymptotes and back intercept.
Okay, so which ones are they?
-1 or 1 and 2, -2 are vertical asymptotes and 7 is nothing.
There we go. Looks good. So these make the bottom 0 but not the top. 7 makes the top 0 but not the bottom. We have yet another example where we didn't have any holes. So no number made the top or the bottom 0. Looks good. All right, go through your number line. Pick your values, get your signs, figure out positive or negative. I think you guys can go from there. Somebody's really thumping outside this morning. All right, so after picking my values and plugging them into our one fraction that we developed, I ended up with negative, positive, negative, positive. Did that work out for you too? We're on the right track? Same track at least? Who knows if it's the right one, but we're on the same one? Okay, so we identified that we want to be below or on the x-axis, so we'll go ahead and take note of those negative intervals. Now we got to ask ourselves brackets or parentheses on those endpoints. So for our first interval, all the way to negative infinity, no way we'll reach it, so we'll do a parenthesis. What about -2? Can I include it? Can I not? We're shaking our heads no. That's good, okay, because -2 was a vertical asymptote. There's no way we have a physical point on our graph to include. At 1, let's see, that was another vertical asymptote, so no way we could include that. And at 7, we said we have an x-intercept, which is technically on the x-axis, and that was part of the description that we said we were looking for. So we can include 7 as an endpoint. So we'll write negative infinity to -2 with parentheses, throw in the u, and then 1 to 7 ending with a bracket. How are we holding up? That one was a little bit more intense because we actually had to develop the fraction itself to compare, but I think we can do that. Okay, we know some fraction properties like common denominator. We just might need some practice with it because it may have been some time since we've done common denominators with with variables at least. Okay, so that's it for this section. We still have a few minutes left if you want to try some homework problems, but we're going to continue with these rational functions tomorrow. Okay, looking at some more properties that they might have.